Hello, everybody. Welcome to another video of Observed Intelligence. My name is hoss.belyadi, and today we're going to talk about some of the visualization basics, primarily in Seaborn. So with that being said, let's get started. Let's start by importing some libraries. Import pandas as PD, import numpy as MP. Let's also import the matplotlib, which is a visualization library. .pyplot as PLT. Also, let's import Seaborn as SNS. And let's also do %matplotlib inline. And this basically allows us to show these plots and figures within Jupyter Notebook. And then let's also set the SNS style, SNS.set. I'm going to set a style of dark grid. I like the style better. You can do white grid, dark grid. It's just the plots look much better, as you'll see in a minute. And let's just run this. I have a database that I'm using from the book from chapter 2. So let's go ahead and import that. Let's just say df is equal to pd.read. And you can import, as you can see here, a list of stuff. If you just hit the tab button, it brings a list of stuff. You got CSV, Excel, HTML, JSON, whatever you want to actually import, you can actually import into Python. In this case, we're going to do a CSV file here. The name of the CSV file is called Chapter 2 Shale Gas Wells Data Set. This is a publicly available data set that we have with the book, and you can actually access online. So let's just do Shift Enter, move on to the next slide. Let's just do a quick, let's just see what's in this table. Let's do a df.head. You can see here you got stage spacing, barrels per foot, or like fluid intensity, well spacing, dip, thickness, lateral length, injection, ISIP, and so on and so forth. And you can always do df.tail to look at the last one, to look at the last, for example, 10 rows of data. You can see here we have 505 wells here, and these are the tail end of the data. So you can also do df.count, for example, and you can see the we have 506 wells for stage spacing, 506 wells. So no data is missing. It's a pretty complete data set in this case. Let's also do a quick df.describe. When you do df.describe, it shows you this table. It's kind of awkward to go back and forth. So let's just add a transpose to that. And here we go. So you can see each of the parameters, stage spacing, wall spacing, lateral length, rate, and so on, and so forth. And you can see the count, a mean, standard deviation, min and max, 25, 50, and 75 percentile, just to give you some idea as far as what's going on. So for example, there are 506 wells. And then you can see the minimum well spacing is 650 and the max is 1350. Okay, so now let's go ahead and try to do some visualization here. Let's just start with a basic distribution plot. So let's just go ahead and say SNS. We're going to use the Seaborn library, and we're going to do SNS.hist plot, and we're going to do df, and let's just pick one of the parameters here. Let's just say I want to plot, let's do well spacing. I can copy and paste it, or I can type it in, is well spacing. And let's do a color of, for example, blue. Okay, and let's also run this. Here we go. As you can see, it's pretty small. So let's just say I want to add a little bit of I want to change the size of this a little bit. So I'm going to do figure is equal to plt dot figure, and I'm going to do fix size. Let's do fix size. Let's just do 10 by 8 for now. See how that looks. Let's run that. Here we go. It looks much better now. You can see it better. You can also add the KDE, like kernel density estimate, to this. Let's just set this is equal to true. It just adds a line to this. And also, you can always change the color to, for example, green. Here we go, change the color to green. You can change it to whatever color you'd like to. Let's just keep it as blue for now, and see how that goes. And then let's just say you also want to change these X and Y axis and also give this a title. So let's just do that. Let's just say plt dot X label. I'm going to the X label is going to be well spacing. Give it a unit of feet. And then let's do plt dot Y label. And let's do count in this case. And then let's also do plt dot title to give this figure a title. Let's just say distribution plot. Distribution plot for well spacing in this case. And let's just run this. Here we go. So you can see distribution plot for well spacing, count, well spacing in feet. One thing that I also like to do is you can always add a font size to this. Let's just say font size. Let's do 20. I'm going to copy and paste this here, and I'm going to copy and paste this right down here. Here we go. So you can change the font size of distribution plot for well spacing, count, and well spacing. So this is a quick way of, plotting a distribution plot. If you actually go back here and change this to, let's just set this to white grid. White grid. If you run this, see, it looks a little bit different now. It's got a white background, but I like the dark grid better. So I'm going to change this to dark and run that. Okay. So now let's just do another parameter. Let's just figure out, let's just copy and paste this whole thing, bring it down here. And what I'm going to do, you can always actually, instead of going all the way up, just do df.columns. It will list all the columns that you have in your data frame. Let's pick another one. Let's just pick prop and loading in this case. And do prop and loading. And I'm also going to change this prop well spacing to prop and intensity. Prop and intensity. And this is going to be pound per foot. And also I'm going to do distribution plot for prop and intensity. Okay. So if you run this, you got your prop and intensity. You can see here, most of your wells were completed between 25 to 3,000 pound per foot to 3,000 pound per foot. And here's your KDE line that you added. You can always do KDE is equal to false, and it would remove that line from a distribution plot. Okay, so here's just how you can add how you can create a distribution plot. Now let's do a scatter plot. Let's do sns.scatter. If you actually type in SC and then hit tab, it will autocomplete for you. Let's do df, and I'm going to do what I like to do actually. Let's actually do a quick calculation prior to that. Let's just do df. I want to do a quick calculation of EUR per 1,000 feet. Right now we have EUR and we have lateral length. So I need to calculate EUR per 1,000 feet. So what I'm going to do is I'm going to say df EUR. The numbers, the EUR numbers are actually in, if you look at this, are the -7 BCF to 22. So to make the numbers readable, I'm going to multiply it by 1,000, and I'm going to divide it by df of lateral length. Let's make sure I don't mistype this. So copy and paste this lateral length here. And here we go. So I have df of EUR per 1,000 feet added now. So if you look at df.head now, you can see there's an additional column that was added, EUR per 1,000 feet, and you can see these are BCF per 1,000 feet. So let's just do a quick scatter plot now, sns.scatter. And what I'm going to do is I'm going to have a scatter plot x-axis of df. Now let's just do, for example, prop and loading for x-axis. prop and loading, and I'm going to do df of EUR 1,000 feet in this case for y-axis. And you can see here, here's your here's your resulting plot. It's basically saying you need to give it x and y to get rid of this red like alarm that it gave you. So let's just add x and y. Here, x and y. So now that red alarm like went away. So let's just actually also copy and paste this guy here to figure size. And I'm going to do, let's add this. Let's just do 15 by 10 in this case. Here we go. Now you can see it much better. Here's a scatter plot. I like the 10 by 8 better. So let's stick with 10 by 8. 10 by 8. You can do the same thing. You can do PLT instead of typing it all in. I'm going to just copy and paste it from here. PLT.x and y. So let's go up here and do x is going to be prop and intensity. Y is going to be EUR per 1,000 feet. Per 1,000 feet. And then this is going to be a scatter plot for prop and intensity versus, or EUR per 1,000 feet. 1,000 feet versus prop and intensity. Okay. Here we go. Let's do that. Here we go. We got prop and intensity, EUR per 1,000 feet, and you've got your scatter plot for EUR per 1,000 feet versus prop and intensity. So here's a distribution plot, scatter plot. Let's also look at a box plot. Let's do SNS dot. You can do type in box and hit tab, and you will give you a couple of options. We're going to choose the box plot. And let's do a box plot of, for example, let's pick a different parameter here. Let's pick a box plot of lateral length in this case. Let's do df. Actually, I need to, here we go, df. And let's do lateral length. Okay. Let's do color of, let's pick red in this case. There we go. It just says give it a x is equal to that. Here we go, x. And just to be consistent with the sizes, I'm just going to use the same size here. Let's just do 10 by 8. Here we go. So you can see this is the lateral length this is the lateral length box plot. Now, what does this all mean? This guy here in the middle, that's the median. Okay, that's the median. This guy right here is your Q1 or 25 percentile. This guy is Q3 or 75 percentile. Okay, if you take Q3 minus Q1 is called your interquartile range. Okay, Q3 minus Q1 is your interquartile range. And then this is in a box plot terminology is referred to as min or minimum. And this is referred to as maximum. It does not mean it's the minimum value in this case. It just in the box plot terminology is referred to as minimum, which is basically your Q1 or 25 percentile minus 1.5 times your interquartile range. And this guy is your Q3 plus 1.5 times your interquartile range. So in the box plot terminology, anything outside of these min and max are referred to as outliers. Okay, so these points are considered to be outliers. Okay, so quick review, you got median, Q1, Q3, a 75 percentile minus 25 percentile, or Q3 minus Q1 is your interquartile range. And then this guy is your min, which is referred to as 25 percentile minus 1.5 times your interquartile range. And this is your Q3, or I'm sorry, this is your max, which is referred to as 75 percentile plus 1.5 times your interquartile range. Anything out of this min and max range, is called the outliers in this case. Okay, so with that, we can also look at another, for example, box plot of another parameter. Let's look at, for example, box plot of porosity in this case. get prosody up. Go prosody, and you can see your prosody box plot right here. And let's also do another plot here called a Violin plot. This is another good plot actually in Seaborn. You can do Violin plot, and let's do df of, let's just pick, for example, prop and loading, and then let's do df of EUR per 1,000 feet again, EUR per 1,000 feet. Let's see how this one looks like. Here's your Violin plot. Let's actually change the size to be the same. So let's bring it down here. And I'm going to just give it X and Y here, just so we get rid of this red notification. Y is equal to that. Here we go. And actually, so what you see here, you can see that prop and loading on the x-axis versus EUR per 1,000 feet on the y-axis. And on this side, you can see the distribution plot of EUR per 1,000 feet. And on this side, you see the distribution plot of prop and loading in this case. So this is one way of doing the Violin plot, which shows you the distribution. One thing that you can also do is let's just copy and paste this, and you can always change the color, by the way, of this to anything that you'd like to. Let's just do color is equal to green. And here we go, I changed the color to green. Let's also copy and paste this real quick. Copy and paste it. Let's add another kind here in this case. Say kind is equal to KDE. And when this is run, you can see the kind of a plot that it generated. It's like a kernel density estimate plot. You can see it. You can generate such plot pretty easily by just adding a kind, which is equal to KDE. Okay, so this is pretty much it for a Violin plot and a distribution plot, box plot. There's another thing called Violin Plot. Let's also cover that real quick, and then we'll call it good for this video. So let's just actually go down here and just say SNS.violin plot, and let's just pick df of, let's just pick another parameter here. Let's just go up here to the table. Let's pick let's do stage spacing in this case. Stage spacing. Let's do color is equal to red. And here we go. Here's actually, let's pick a different parameter that I can explain what a Violin plot is. Let's pick well spacing so we can see it better. See these things much better. And I'm going to add this is equal to X is equal to that. So we get rid of that. I'm going to also add this size here to help us see this better. So here we go. Here's the size. Maybe change this to 15. There we go. So this is, you can see here's the Violin plot. You can always go down and do plt.x label, plt.y label, plt.title, and add, just play around with the font a little bit too if you'd like to. But for the sake of this, a Violin plot, you can see this. This is another visualization plot that you can use to show the nature of your data. So in this case, this white dot in the middle, if you look closely, this is your median, where the solid black, or where this solid black line ends right here. That's your Q1, where my mouse is. And this is your Q3, or 75 percentile. And then where the lighter black line ends, that's your min or minimum, which we discussed in the box and Violin plot terminologies. Minimum is referred to as Q1 minus 1.5 times your interquartile range. And then where this solid or this light black line ends, that is your maximum, which is not the maximum value, it just means Q3 plus 1.5 times your inner quartile range. And anything outside of this is called your is basically called your outliers. These are your outlier data, which you can see much better in the box plot right here, for example, as compared to here. But one of the advantages of Violin Plot, you can see the humps a little bit better as far as where most of your data lies. So for example, if you look at the distribution plot of your well spacing, let's look at distribution plot of well spacing. You can see most of the data lies here between 7 to 800 feet. If you go down here, you can see between 7 to 800 feet, that's where most of the data lies. And also you can see your median, Q1, Q3, Q1 minus 1.5 times your inner quartile range, Q3 plus 1.5 times your inner quartile range. Okay, so you just feel free to play around and play around with this data set and just plot other parameters. You can always, let's do one more and then we'll finish the video here. Let's do ISIP, instantaneous shut-in rate. Let's pick that one. And let's just do, ISIP, and you can see here a Violin Plot. You can see you got data that had an ISIP of 5,000 feet. And then you had data that had ISIP of close to 8,000 psi. So 5,000 psi versus 8,000 psi. Okay, so hope this was helpful. If you liked the video, please like and share on social media, and also like and share our channel Observe Intelligence on YouTube. Thank you for watching, and we'll see you guys in the next video.